Let's move on and take a look at circular orbits, because in circular orbits, gravity acts as the centripetal force. So gravity causes orbits. It causes the planets to orbit stars. It causes the moons to orbit planets. And it also causes satellites to orbit Earth. Here is a picture of a satellite orbiting the Earth. Clearly this drawing is not to scale. But let's take a look at a few important things. We see that gravity is acting towards the center of the Earth, and we know Earth's gravity is always acting towards the center of the Earth. This dashed circular line, this is known as the orbital path. This dashed line is the radial dimension, and this dashed line here is the tangential dimension. Notice that the gravity force lies on the radial dimension, and it is unbalanced. It is the only force acting on the satellite, and so the gravity force fits our definition of the centripetal force. Now, I want to point out orbits are elliptical, but most are nearly circular. So we're going to treat this satellite orbit as being perfectly circular. Also, just as a point of information, while Earth's orbit around the Sun is elliptical, it is nearly circular. In fact, if you looked at the Earth's orbital path drawn to scale, you would think it was a circle. You would not be able to tell that it was elliptical. Let's look at a few key terms and relate them to some of the key terms we've learned about circular motion and centripetal force. First, we have the orbital velocity, and it is the tangential velocity of the object because it's moving in the tangential dimension. Next, we have the orbital altitude. That's the distance between the surface of the planet or star and the object. In this case, the orbital altitude is the distance between the Earth's surface and the satellite. Not to be confused with the orbital altitude is the orbital radius, and that is the distance between the center of the planet or star and the center of the orbiting object. In this case, it's the distance between the satellite and the center of the Earth. Let's discuss a few concepts about circular orbits before we get into the quantitative analysis. So conceptually, we have to recognize that the gravity force gets weaker as objects move away from the center of the planet or the star. For instance, Earth's gravity is much stronger on the surface of the Earth than it is if we're hundreds of thousands of kilometers away from the surface of the Earth. And because the strength of the gravity force is a function of how far you are from the center of the Earth, each orbital radius has a unique fixed gravity force. And this is determined by Newton's law of gravitation. We're not going to get into that in this unit. We will cover that in our unit on gravitation. Therefore, each orbital radius has only one possible orbital velocity. Satellites that are orbiting about the same distance above the Earth's surface are all going to be traveling at about the same orbital velocity. Finally, the orbital velocity decreases as the orbital radius increases. So satellites that are orbiting further away from the Earth are going to be moving slower than satellites that are orbiting closer to the Earth. Let's get into the quantitative analysis now. And of course, we're going to use Newton's second law, adapt it for circular motion. And that is the centripetal force is equal to the mass times the tangential velocity divided by the radius. And let's just be clear, in this case, the gravity is the centripetal force measured in newtons. The object's mass is the mass in kilograms. The orbital velocity is the tangential velocity in meters per second, not kilometers per hour or kilometers per second. And the orbital radius, not the orbital altitude. The orbital radius, not the orbital altitude, is the radius in meters, not kilometers. So there's two things when dealing with this R. First of all, you want to use the orbital radius. That's measured from the orbiting object to the center of the Earth. you do not want to use the altitude because that's measured from the surface of the planet to the satellite. And also, because these distances are so large, you will usually be given the orbital altitude or orbital radius in kilometers, but you must convert it to meters when you use it in the equation. Let's go ahead and solve a problem. So in this case, we have GOES 16 is a 2,857 kilogram weather satellite that orbits Earth 35,786 kilometers above the surface, so that's the orbital altitude. Now we need to add the radius of the Earth to get our total orbital radius, and when we do that, we get 42,157 kilometers, and that's because the Earth's radius is 6,371 kilometers. So we add the 6,371 kilometers to the orbital altitude, and that gives us the orbital radius, which is measured from the Earth's center. The gravity force acting on the satellite at this altitude or orbital radius is 640 newtons. So in part A of this problem, we're asked to find the satellite's orbital velocity. So we're going to take our Newton's second law and we're going to rearrange it to solve for the tangential velocity. So we go ahead and rearrange it, and then we plug in our gravity force. We convert our orbital radius to meters, and we divide it by the mass of the satellite, and we take the square root of that result, and we find out that the orbital velocity for this satellite is 3,073 meters per second. That's about 7,000 miles per hour. Part B, how long does it take to make one orbit? And here is an important hint. We need to remember that the circumference of a circle is 2 pi r. So even though we're talking about a circular orbit that's huge, it's still a circle. And so the length of this orbit, or the length of one orbit, is 2 pi r. Also, we need to recognize that the amount of time it takes to make one orbit is known as the orbital period. And so the formula for the orbital period, capital T is the symbol for the orbital period. It is equal to the circumference of the orbit divided by the tangential velocity. And of course, we know the circumference is 2 pi times the radius. And now we go ahead and plug in our orbital radius in meters, and in the denominator we put our orbital velocity that we calculated in part A, and we find out that it takes 86,196 seconds to make one orbit. That's not too meaningful to me in seconds, so I always convert this to hours, and it's 24 hours. This satellite moves around the Earth at the same rate the Earth spins on its axis, because the Earth makes one complete rotation in 24 hours. When the satellite is revolving around the Earth at the same rate the Earth is spinning, we call that geosynchronous orbit. If this orbit is above the equator, and in the case of the GOES 16 it is above the equator, we call that geostationary. In other words, that satellite is going to be above the same spot of the Earth all the time, because as the Earth is spinning, the satellite is orbiting at the same rate. Well, that's just an interesting fact about satellites. There's all different types of satellites, and based on their function, they'll orbit at different levels. There's 3 general classifications. There's low Earth orbit, there's medium Earth orbit, and there's high Earth orbit. Our weather satellites and communication satellites are in what's called high Earth orbit. GPS satellites, on the other hand, are in medium Earth orbit, so they would orbit closer to the Earth than a weather or communications satellite.